可以吗 ？OK， 好。Okay, so what is coherence D? Okay, coherence D is like this. The definition, like this. Okay, for two given groups. Okay, assuming their mu and the sigma are mu1, mu2, and the sigma1, sigma2. Okay, respectively. Okay, then their coherence D. The D actually stands for distance. Okay, D actually stands for distance. Okay, so obviously, okay, what you want, I mean, the difference of the mean is important, right? I mean, we want to measure like differences between two groups. However, okay, how significant is this difference of means? Okay, is also determined by their standard deviation. Okay, because for example, like if you have like difference of 1, then if the standard deviation is in the at the scale of 0.1, then you should consider this difference is large. But if for the same difference of mean, okay, if the standard deviation is at a range of 100 or 10, okay, even 10, then that difference, okay, of mean will be less significant. Okay, so that's why, okay, this coherence D is defined by in this format. Okay, so we compute this pooled standard deviation and use that as like a denominator in the coherence D to represent like to normalize the difference of the mean. Okay, basically. So coherence D is a way to measure effect size. Okay, where difference of the mean are standardized by considering the pool standard deviation of the both group. So I already explained. Okay, so yeah, so including the intrinsic variations of group is a way to put the differences in context. Okay, so rescaling, okay, the differences help us make sense of the importance of difference between groups. Okay, even when we are not very familiar with the scale used, I mean, for the measurement. So this is like how coherence D works. Okay, in some sense, coherence D, okay, can also be interpreted as a z-score. Okay, do you guys know what z-score is? Z-score is like okay, you see how the difference of two values, but you measure it by by the number of like standard deviation. Okay, so for example, in one distribution, okay, you get like two values. How far away, I mean, do you consider these two values? Is you just consider the distance of these two values divided by the standard deviation of the distribution. So if the difference is like only like maybe 0.1 standard deviation, that's not much. But if the difference is maybe like 1 or even 2 standard deviation, that's considered a lot. Okay, so in some sense, coherence D, okay, is similar, right? Because you are dividing the difference of mean by like kind of like the scale of the standard deviation. So it's also similar to the, I mean, conceptually similar to the z-score. Okay, so So when the differences of mean are standardized, okay, just like Cohen's D, okay, we may still need to calibrate ourselves based on the context of a given problem to be able to say if a given value is big, small, medium, okay. So this calibration can be acquired with enough practice, okay. For example, okay, if I used to perform several analyses for more or less the same type of problems, okay, we can get used to a Cohen's D, for example, 1, okay. So when we get a Cohen's D of 2, then we know we have something important. So basically, okay, if you do this similar problem, if the previous Cohen's D is a small value, and this Cohen, now you get a larger Cohen's value, then you know this value is more significant than the previous one. So it's more like a result of the comparison, okay. If you do not have this practice yet, so you can ask a domain expert, okay, for their variable input. Again, because every time you see something, it's like based on the, for example, context of the problem, then you probably it will be a good idea, okay, to consult a domain expert, okay. So, for example, like a very nice web page to explore like a difference value of Cohen's D. You can check out this web page, okay, to get a more understanding of the Cohen's D. But if you don't have access to a domain expert, then you probably have to do more experiments, and through the comparison, you can get a sense of like which Cohen's D value. I mean, obviously, a larger Cohen's D value, okay, means a more important impact for a particular factor that you consider, okay. So that's like the Cohen's D, okay. So another, okay, way to report the effect size is the probability of superiority. Okay, what is probability of superiority? Okay. Okay, intuitively, okay, the meaning of probability of superiority is defined as the probability that a data point taken at random from one group, okay, has a larger value than another value taken at random from the second group. Okay, so you just randomly take value from two groups, okay, and then you compare these two values, okay. So that's the probability of superiority, okay. But we know this is difficult to calculate, but actually, if you assume the data is distributed as a normal distribution, which is, a lot of time if it's not exactly normal, but it can be approximated by a normal distribution, okay? If that's the case, we can compute the probability of superiority from Cohen's D, okay, using this expression, okay? In this equation, okay, this is probability of superiority, okay? This delta, okay, is the Cohen's D, okay? And this phi, okay, is the cumulative normal distribution. Okay, it's another distribution that is well known. Okay, if you know normal distribution, the cumulative normal distribution is, related to normal distribution, but it's like it's represented by like an integral of a normal distribution, basically. Okay, so this I already explained what the data is. Okay, so you can see if you have the delta, you can get the probability of superiority from this formula. Of course, with the understanding that the model, okay, or the distribution is normal. Okay, this is assumption. Okay. So we can compute a point estimate of the probability of superiority. okay? Or we can compute the whole posterior distribution of the values. So this is one way to compute just a single estimate of the probability of superiority. But if you want, we can also use we can also compute the whole posterior, the distribution of the probability of superiority. Okay. So if we are okay with the normality assumptions, this normality assumption, as I said, okay, it works a lot of time. Because a lot of models can be approximated by normal distribution. Okay, so we can use this formula to get the probability of superiority from coherence D. Okay, otherwise, as we have samples from the posterior, we can also direct compute the coherence D. Okay, so of course you don't compute this thing by hand. You compute this thing by the program. Okay, so it's not that difficult. Okay, just use the program to do the job. Okay. So here, okay, we are, looking at another example. So this example is sort of interesting. Okay, because in Taiwan, when you go to a restaurant, the tipping is at the fixed rate, right? Either the restaurant does not take tip, okay, you just pay for whatever you order, okay? Or, okay, if the restaurant take tip, okay, they will just add that value, add that percentage directly in your bill, right? Okay, for example, if you spend $100 for your meal, okay, you will see the bill may be 110, right? In there, okay, the $10 represent the tips, right? Okay, so that's the situation in Taiwan, but this is not the case in U.S. Okay, in U.S. it's customary to give tips, okay, but the tip, okay, the amount of tips depends on the quality of the service. Okay, so if you like the service this restaurant provide, okay, you can give more tips. Okay, if you don't like the service, okay, you can even give 0 tip, which represent you don't like their service. Okay, this is an indirect way to tell the restaurant that their service sucks. Okay, but in Taiwan, we don't have this system. Okay, so but anyway, of course, in US, the tipping percentage, if you get when I was in US a long time ago, the percentage of the tipping, okay, for example, for lunch is normally 10%. Okay, if the service is reasonable, okay, reasonable is normally 10%, okay, or close to 10%. If it's dinner, then it's normally 15%. I'm talking about in general. I'm not saying this is a written rule, but I'm saying okay, if you feel okay, the service is reasonable, it's okay, and you as I said, because tipping is sort of mandatory in U.S., so you have to tip. So you just calculate this amount as your tips. Okay, but obviously, this study is interesting. Okay, because this data was reported, okay, first time by these two researchers in 1995 in Practical Data Analysis, Case Study in Business Statistics. This is a journal paper, actually. Okay, so in this paper, they want to study the effect of the day of the week on the amount of tips at the restaurant. Okay, so basically, they observe on different days, if the tipping behavior will change or not. Okay, so of course, in this case, the different groups will be different day, okay, of the week, different days of the week, okay. So there's no control group or treatment group because, well, we just break the result into different number of days, different days. So if we wish, we can arbitrarily establish one day, okay, for example, like Thursday as the reference or control, okay, but well, we don't have to, okay. So this is the data set, okay. I mean the CSV. Oh, by the way, I told you guys like all the program as well as the data set of this textbook can be downloaded, right? Okay, I mean you can just check out like the book and I think in the preface or somewhere it tell you like where to download all the data. Okay, so yeah, so this is the data. Okay, tips.csv. So you read. Okay, you put you just got this data and store in the tips. Okay, and then tips.tail just output the last few entries of this data set, and it looks something like this. Okay, the last 5 entries look like this. Okay, what we are interested in are this one, the tip, and the day. Just these 2 columns. The other the other columns do not. I mean, doesn't matter. Okay, the other columns do not matter. Okay, I mean, of course, if you study